This lecture is about design of reinforced concrete beam for shear, and the topics that will be addressed includes shear resistance, shear stresses, sorry, not resistances, shear stresses in rectangular beams, diagonal tension in RC beams subjected to flexure and shear loading, types of cracks in reinforced concrete beam, shear strength of concrete, web reinforcement requirement in reinforced concrete beams, ACI code provisions, and example. The lecture will be divided in two videos for better understanding and complete explanation. Okay, so starting with the concept, the shear stresses in rectangular beam. Shear stresses in homogeneous elastic rectangular beam. The shear stress rho at any point in the cross section is given by a very popular and familiar formula that you have studied in mechanics of solids or strength of materials. Shear stress is equal to VQ divided by IB, where V is the shear force at that section, I is moment of inertia of cross section about neutral axis, B is the width of the beam, and Q is statical moment about neutral axis of that portion of cross section lying between a line through point in question parallel to neutral axis and nearest face. Okay, so you know Q very well. It is, for example, if you are considering the uh, area A, B, C, D, okay, so the area of this element multiply by the distance between its centroid and the neutral axis of the beam. So this is called Q, right? So if the line CD is at AB, the area will be 0 and this term will be 0, and if CD is at neutral axis, so the area will be maximum and Q will be maximum, right? So accordingly your stresses are 0 at the edges and maximum at the center, because at any particular cross section the shear force is constant, right? There is one shear force along the beam at the specific cross section at a specific point. The B of the beam, width of the beam is constant, depth of the beam is constant, so all the three properties are constant. The only one thing that is varying along the depth is this Q, and Q is the distance, Q is the distance of the line or the area from the neutral axis, so you have to multiply the area and the distance from the centroid of that area to the neutral axis of the beam. Other thing is that you always take the area between the line or the point where, of interest and the nearest edge of the beam. Okay, so for example, if you are talking about line CD, so you cannot take area of between line CD and the neutral axis, you cannot take this area. Okay, always if your line CD is lying on this side of the beam, so in that case your area will be between line CD and, for example, this is your line CD, so this will be your area. Okay, so it is always, the area will always be taken as the uh, area between the line and the nearest edge of the beam. I hope you understand this very basic concept. So for the calculation of shear stresses at level DC, for example, this is level DC, right? In the given figure, Q will be equal to area of this ABCD as I explained on previous slide, and the y dash, which is the moment arm of area ABCD, right? For shear at neutral axis EF, this is the neutral axis. So what will be the value of shear force? You can take a area between EF and AB or EF and this edge of the beam. Okay, so either can be taken as Q. So Q is equal to area of ABEF multiplied by, for example, total height of the beam is H, so height of this side will be H by 2, and we take the distance from centroid, So it will be h by 4, the distance between the neutral axis and this point. Okay, I is constant bhq by 12. Therefore rho is equal to vq divided by ib. Put the values of q and I, so you get v or rho maximum is equal to 3 by 2 of v divided by bh. Okay, so at neutral axis you will having maximum shear stresses, and what will be its value? It will be 1.5 times v divided by bh. Okay, so we, b, what is b is width, what is h is height. So your cross sectional area, shear force divided by cross sectional area is the shear stresses, and 1.5 times your average shear stresses is the maximum shear stresses. Okay, shear stresses in RC beam. The shear stresses in reinforced concrete member cannot be computed from this equation because concrete is not an elastic homogeneous material. Concrete is inelastic material. Concrete is non-homogeneous, or you can say that it is a heterogeneous material. So it cannot be applied to concrete directly. So tests have shown that the average shear stress in a RC beam can be expressed as rho average is equal to V divided by BD. If you remember on the slide, previous slide, it was 3 by 2 V divided by BD, and I told you that V by BD is the average shear stress. Okay, so the maximum value which occurs at the neutral axis will exceed this average by an unknown but moderate amount. Okay, so this is your average shear stress value V divided by BD shown by the dotted line. Okay, and at the neutral axis V maximum will exceed it, but it is not known that how much amount. Okay, but moderate amount, but the amount is not known. Okay, now considering the diagonal tension in RC beams subjected to flux and shear loading, consider this as a simply supported beam under a uniformly distributed load. This is the neutral axis. You have taken two elements, one exactly on the neutral axis and the second one is on the tension side. Okay, so consider the first element at neutral axis, there is no tension, no compression. So see, there are no tension and compressions on the element, there is only shear force. So if a downward force is acting on the right face of the component 1, element 1, then to balance it, upward downward force and upward will should act at the left face of the component. So summation of f of y is equal to 0 satisfies. V is acting downward, so V is acting upward, right? This is your vertical shear. Now to balance this, because this vertical shear is making a causing a moment or couple, okay, and trying to rotate this element 1, but to uh, keep it in equilibrium, an anti-clockwise movement should act with the same value of v and acting at a same perpendicular distance. So as a resistance of vertical shear, there is a horizontal shear in the element, and this element is subjected to pure shear condition, right? I hope you remember your lesson from your mechanics of solids or strength of material subject. Okay, now if you observe, you will see that this force and this force is trying to stretch this corner, right? Similarly, this force and this force are trying to stretch this corner. Similarly, both these forces are trying to compress this corner, and these two forces are trying to compress this corner. Okay, so it's tension in this side is acting on the element, and compression is acting in this side. So we just rotate the element and we apply the compression forces. See the compression in this diagonal, so compression is acting in this direction and tension is acting in this direction at this element, and we have rotated it 45 degree. Why? Because both the perpendicular and base have same values, so it will be making 45-degree angle. Okay, now consider element 2, which is on the tension side. So in addition to the shear forces, see the forces, shear forces acting on element 1 are there, and in addition to that there is a tensile force, see F. So to balance this tensile force, the same amount of force should be acting on the other face of the element. So now, in the same way, you want to uh, make this figure that okay, I just want to remove these shear forces, and I want to find out the principal plane and principal stresses. So at principal plane there is no shear force and only normal forces are acting. So in order to rotate that element, in this case you can get exactly the same configuration of tension and compression, but the one thing that is changed or different is, in this case you don't know the amount of angle and you have to determine it by calculation. In the case of pure shear, it was known that it is exactly 45-degree, but when you are moving away from neutral axis upward or downward, then this angle is different, it is not exactly the 45-degree. Okay, now types of cracks in reinforced concrete beam. There are two types of cracks: flexural cracks, which are vertical. For example, look at these cracks. These are flexural cracks acting at the middle of the beam where there is a maximum positive bending moment. Okay. And second one is diagonal tension cracks. And these diagonal tension cracks can be of two types. The web shear cracks. These cracks are formed at locations where flexural stresses are negligibly small and the shear forces or shear stresses prevails. Okay, and flexure shear cracks. These cracks are formed where shear force and bending moment both have large values and they cause the beam to crack. So look at this figure. These are the flexural cracks. These are the shear cracks, and crack like for example, this one. These are flexure shear cracks that they are initially vertical and then move at a certain angle like this one. Okay, so these are flexure shear cracks. Having said that, why is the web reinforcement requirement in RC beams? It says that nominal shear capacity of reinforced concrete beam can be given by this equation, which says that the nominal capacity is equal to capacity of concrete plus capacity of steel, where Vc is nominal shear capacity of concrete, Vs is nominal shear capacity of shear reinforcement. Note that in case of flexural capacity, Mn, it was equal to Mc plus Ms, and we took Mc is equal to 0 at ultimate load. Why? Because we assumed that in tension the strength of concrete is ignored and only steel is acting in it. However, in shear, we consider the shear capacity of concrete and we do not ignore it and we do not consider it to be zero. Okay, so keep in mind that it is different than flexural design. In flexure, the concrete was only taken in compression and ignored in tension. However, in shear, the concrete of the entire cross section is considered. Okay, and its shear strength is taken into account. Test evidence have led to the conservative some assumption that just prior to failure, means just before failure of a web reinforced beam, three internal shear components contributing to the total shear, the sum of which is referred as a shear capacity of concrete. So at previous slide you have seen that Vn is equal to Vc plus Vs. Now out of that we are just talking about Vc, that okay, what is the shear capacity of concrete itself. So it says that tests have given us different assumptions, conservative assumptions, that just prior to failure the shear uh, capacity of concrete comprises of three internal shear factors. So in the equation you can see that Vc is equal to Vcz plus Vd plus Viy. And what are these components? Viy is equal to vertical component of sizable interlock forces. So you have coarse aggregates in your beam, and the crack is happened, and different aggregates, for example in this section and in this section, they are interlocking and resisting each other. So they have considered that okay, one component is due to that interlocking of the aggregates. VCZ is the internal vertical forces in the uncracked portion of the concrete. For example, the crack has initiated here and it is propagating through this and it reached up to this point. And this portion of concrete is uncracked. So VCZ, you can see that the compression is here, okay? And Z is the depth of this portion. So VCZ is the capacity of this uncracked concrete section. And the third one is VD, which is the internal vertical forces across the longitudinal steel acting as a dowel. So if you remember from the flexural design of beam that you provide tension reinforcement in the beam. So this dowel action, this reinforcement that is continued and the crack is passing through this reinforcement. So this dowel is this rebar is acting as a dowel action and it is resisting the shear to prevail, and it is contributing to the shear capacity of concrete. So tests have supported that these three factors can be taken into account while determining the shear capacity of concrete. Again, coming to the equation, Vn is equal to Vc plus Vs, and we determined the value of Vc according to ACI 22.5.5.1. Vc is equal to Vcz plus Vd plus Iy. We know this thing from previous slide, and this gives it equal to 2 under root Fc prime Bw into D. So you can directly find out this value from this formula, okay? And the table is given in the figure as well, where Pw is equal to width of beam, D is effective depth of beam. It is important to mention here that this value of shear strength of concrete exists at the ultimate, that is just prior to the failure condition, okay, and it is not just from the beginning, so do not confuse it. Also there are some requirements of AV minimum by ACI 10622, that you have to provide minimum area of steel in the shear as well, and we will discuss it later on. So from previous slide, we concluded that Vc can be found out by using the equation provided by ACI, and now we are left with Vs, that is the shear capacity of steel, okay. Now keep in mind that Vs is equal to N AV into Fy. You know a Fy, okay, the yield strength of steel. The number of stirrups is the N. This is the stirrup that you are providing in the vertical direction. See, you remember the longitudinal steel or flexural steel is provided along the length of the beam, right? And the shear steel is provided perpendicular to the longitudinal axis of the beam. See, this is the direction that we provide stirrups in, spaced a distance s apart. So the distance between two stirrups is s. On the length p, this is length p of the crack. For example, the crack initiated here and it is propagating through this length and reached this point. The total length of the crack is p. So how many stirrups will be in this length of p if we are given the spacing of these stirrups? Hence n is equal to p divided by s. So if we divide this length divided by this distance between the stirrup, we will get the number of stirrups, as that how many stirrups are required in this crack length. This length p is conservatively assumed to be equal to the effective depth of the beam. So it says that the effective depth, for example distance of the tensile steel, this effective depth is equal to this length of this crack, okay. Thus n is equal to, here n is equal to p by s. So we have assumed that p is equal to effective depth, so you can put d instead of p. So n is equal to d by s. You know d, you know s, so you can determine n. You just take the value of n and put it here and you can determine the value of vs, okay. Therefore vs is equal to, you just use these values, av, Fy, and instead of n you use d by s. So this is the formula, Vs is equal to Av Fy d by s, and it is from ACI 318 22.5.8.5.3. So this is how You determine the shear capacity of concrete and steel. Now coming to the design shear capacity of reinforced concrete beam. So uh, as we talk about design, so we always provide the strength reduction factors. Phi Vn is equal to phi Vc plus phi Vs. To avoid shear failure, this phi Vn should always be greater than or equal to Vu, which is the shear demand. Okay, and it comes from the analysis value. This is your design value. So if we take consider phi Vn is equal to Vu, then these two phi Vc plus phi Vs should be equal to Vu, and phi Vc is equal to phi, we know Vs values, AVFy into d by s is equal to Vu. From here we can find the value of s, that okay, what is the spacing requirement for a certain demand of shear force or shear stresses. So this equation directly gives you the amount of or the spacing of the stirrups. If you know the area of the stirrup bar, for example number 3 bar is used as stirrup, so you know its area, you know Fy, depth of the beam is known, Vc can be found out by ACI equation, Vu will be given from the analysis, so you can directly find the spacing. And keep in mind that the strength reduction factor phi for shear is 0.75. Okay, now it says that AV is the cross sectional area of web reinforcement within a distance s. For single loop stirrups, two legged, AV is equal to 2 times area of bar. Okay. For example, if you see you have provided stirrups in this manner, right? This is your stirrup. Now, to resist the shear, this leg of the stirrup is acting, as well as this leg of the stirrup is also acting. So the area of bar should be multiplied by 2 to get the area of stirrup. Okay. So it is two-legged stirrup, vertical stirrup. At section AA, this is section AA, if number 3 bar is used, so area of bar is 0.11 square inches. However, the area of stirrup or shear area should be taken as 2 times 0.11, that is 0.22 square inches. Okay. Now locating the critical section for critical shear Vu. In most of the cases for the design of shear, critical shear is taken at a distance d from the face of the support instead of maximum shear. Okay, so why we take at a distance d, because the crack, we assume that the maximum shear is acting at the support, at the face of the support, and we also know from previous concept that the length of the crack p is equal to depth of the beam. So it says that the length of the beam will the length of the crack is d, and this is the critical point where critical shear is acting and it is causing shear cracking in beam. So we design for this critical shear instead of ultimate shear. Okay, and for different support conditions, this is the location of the critical shear Vu. For example, consider this. So from the face of the support at a distance d, critical shear is acting. Similarly, in this case, from the face of the support, critical shear is acting on both of the beams. Similarly, in this case, from the face of the support, in this case, from the face of the support, not at a distance t. Why? A beam loaded near its bottom edge. Okay, so the load is at the bottom edge, not at the top of the beam. Keep in mind. So it is an inverted T beam. So here you have to take it at exactly at the face of the support and end of monolithic vertical element. So here also you do not take at a distance d. So in case A, B and C, you take it at a distance d or within a distance d, and at D and E you take it at the face of the support. So figure A and B are the more frequent conditions that we use in the civil structures, while the figure C, D and E are the special conditions. Okay, this is the shear force diagram, and as you people know that for a uniformly distributed load, the shear force diagram is same, and after for example, for a simply supported beam with a UDL load, the shear force diagram is like triangular configuration up to midspan. It is 0 at the midspan, and it is similar in the other side. Okay, so a typical half shear force diagram for a simply supported beam subjected to UDL is shown below. This is the positive side of the shear force diagram, and you know that there is no difference in positive and negative shear since both are acting vertically, and we have provided stirrups for both of them in the vertical direction. So it is not like flexure that you have to be careful for positive and negative. Okay, this is half shear force diagram. The critical shear VU, this is VU, which is the critical shear. Okay, the concrete capacity phi VC is plotted also on this diagram, and phi VC divided by 2 are plotted on the diagram. For example, you have performed the analysis, you got the value, uh, and you determined the critical shear value VU. Okay, VU is, for example, 200. Now, from the ACI equation, you have found the value of phi VC, and that is, let's suppose, 100. So you have plotted 100 phi VC, and phi VC divided by 2 is 50. So you have plotted 50. That okay, here is so this is the length of the beam, right? You know that. Now what it says that based on these values, three conditions are possible. That phi VC is greater than or equal to VU. It says that this phi VC could be greater than VU. For example, VU is 200 and you get phi VC equal to 300. The second one is phi VC is less than VU. For example, this is the case that phi VC is 100 and VU is 200. And the third case is phi VC divided by 2 is greater than VU, which is the case here. Okay, so now let's discuss these three cases. Okay, so the first case is when phi VC divided by 2 is greater than VU. So if phi VC by 2, half of the concrete capacity, is greater than your critical shear, then no web reinforcement is required. And you do not need to provide any shear reinforcement in beam, where VU is the critical shear taken at a distance d from the face of the support. The second condition is when VU is greater than phi VC divided by 2, but is less than phi VC. For example, phi VC divided by 2 is 50 and phi VC is 100 and your VU is 75. So it is in between both of them. Okay. So theoretically, no web reinforcement is required. However, ACI 10622 recommends that minimum web reinforcement in the form of maximum spacing shall be minimum of. It says that the minimum value from these four should be provided as a shear reinforcement. So these are the four equations. AV is a stirrup area, Fy you know, Bw you know, D you know, and all these factors you know very well. So these are the two conditions where VU was less than half of the capacity, and second one greater than half capacity but less than concrete capacity. But these two conditions rarely happen or maybe never happen. The third condition is the important one. Most of the times, or if I say that all the times, this condition prevails when phi VC is less than VU. You are required to provide web reinforcement, and required spacing is determined by this formula. If SD, this SD is greater than S max, then use S max. And you know the formula for S max. See, it says that if your SD is 15 inches and the least value from these four is 12 inches, so do not provide these 15 inches, provide 12 inches. Okay, so minimum spacing as minimum is 3 inches. You cannot be chosen as less than 3 inches. You cannot provide stirrups for 2.5 inches or some or anything. Okay, because of many issues, and the important one is workability. So we have seen the three conditions. Phi VC, we have compared it with VU and we got three conditions. The fourth is check for depth of beam. If phi VS is less than phi 8 under root FC prime BWD, then depth of beam is okay. If not, then revise the depth of beam. If this is greater than, then increase the depth of beam. Okay. And the fifth is check for spacing. If phi VS is greater than phi into 4 under root FC prime BWD, this was 8, this is 4. Divide spacing of S maximum that you got previously by 2, otherwise use as maximum. Okay, so reduce the spacing if it is not okay. So what we have discussed previously is presented here, so for better understanding, that this is 5 VC divided by 2. Since in this portion the shear is less than 5 VC divided by 2, so theoretically no stirrups are required till this point, okay, in the center of the beam. Now when you are going further to the VU, in this portion your VU is greater than 5 VC by 2 but is less than 5 VC, so here provides stirrups at maximum spacing. And in this portion when your VU is greater than 5 VC, so use the design spacing of the stirrups. Okay, this is what I explained here. And with this we are done with the concepts related to the shear design of reinforced concrete beam, and now we will solve an example, but that will be done in the second part of this video. I am just completing this, and will show you the example in the second video. Okay, thank you very much.